Thanks very much for the opportunity to speak. So this is about joint work with Nathaniel Arcor and Joanna Coe. It's got connections to lots of things. Today I learned from Sandra Mantovani's talk that will be related to these off-fiber fibrations. And so what are they called again?
Depends what. Cartesian is one.
Okay.
The other is the Cartesian monoid.
Okay. But so what's it about? So classically, limit sketches, you can capture things like groups or rings, or if you use pullbacks, small categories, stuff like that. So they're great. Everybody likes them. So if you want to capture things like categories with structure, you would think that you want to use some sort of two-dimensional limit sketch. And so this works very well, but it sort of breaks down surprisingly in it. I mean, not completely, but some aspects of it do, and they're not totally obvious. And so to sort of solve these aspects, what you need to do is move away from two categories to two categories with some additional maps, so special maps. So people consider these in other settings as well, like these tribes and stuff, and it's a bit different, but it's a bit similar as well. So but so we have to move away from two-dimensional limit sketches to enhanced ones. So that's the story I'm going to tell you about. So where does the problem arise? So very simple place that we look at internal categories. So I think everyone knows what an internal category is, but there they are. And so you've got your nice source and target maps, your pullback projections, and your structural maps, the M and the I, satisfy a few laws. In sets, these are small categories. Everything works very well. So if we look at what the morphisms between them are, the internal functors are the things you would want. They just preserve everything. So they're like the natural transformations in a sense that you can make precise. I won't make precise exactly now. And then set, these are functors. So that's great. So if we want to look at two categorical structures, you move to models in CAT, say. That's a good place to start. So if you look at an internal category in CAT, you get a double category. And so here you've got a category of objects and arrows. You can call them horizontal, say, and then vertical arrows and squares. So a square is something like this, and you have its source and target. There'll be some horizontal arrows, and then you have all these compositions and so on. I think people have seen these before. And in the internal functors now are the strict double functors, the things that preserve everything in the strictest possible sense. So the fun starts to emerge when you look at what the weak maps between them are. So you've got like lax double functors. But the funny thing about these is that they still preserve the boundary of squares, right? To preserve the appropriate shapes of things. So that means that they actually commute with the source and target projections. So you've got some strict commutativity here. But they only commute with the structural operations in a laxer sense. Like this. So, but if you think about what you actually get, then you get so it's like a lax natural transformation, but whose components are strict at the source and target projections, and also the pullback projections. Okay, but so we see here that we've got something weird going on, which is that we've got a mixture of laxness and strictness. So what we see is we need to treat these sort of source and target projections and the pullback projections as special in some sense. Okay? So I read like a straight arrow for a special one and a wiggly arrow for a general one. So this is the idea, and of course that's very natural because the M and I here are some sort of structural operations. The other ones are kind of simple. But okay, so we see a diagram like this start to emerge. And then you see diagrams like this if you look in lots of places when you start to look. So if you know about the notion of a monoidal double category, for example, so there now there are pseudo-double categories, but things like spans and profunctors with a compatible monoidal structure. Okay? But what does that actually mean if you look at it? It amounts to an internal, now pseudo-category, there's no real difference. In the world of monoidal categories and strong monoidal functors, but where you require some of the maps to be strict monoidal. Okay? So you see exactly this sort of diagram again. Okay? And or you can view it, say, as a pseudo-monoid in the world of pseudo-double categories and pseudo-double functors. But again, these product projections are strict. Okay, you can say that's sort of, that's what you need, that's what you have. So we see that instead of the summary so far is somehow what this is telling us is that we need to move from diagrams like this to diagrams like this. Okay? And that's the idea of moving away from, so a diagram like this lives in a 2 category if we had the pseudo double category version, because then things would only commute up to invertible 2 cells. But diagrams like this live in what's called an enhanced 2 category or an F category. And that's what pushes us to enhanced 2-dimensional limit sketches to capture these sorts of structures. And so this is just the intro, and then the more formal stuff we can get into now. So these were introduced enhanced 2 categories. So the simplest thing you could have by Lack and Shulman. So they're just 2 categories with a sub-collection of morphisms called tight, containing the identities enclosed under composition. Okay? So general morphisms are called loose, and we draw them like this because you're thinking, the idea is you're usually thinking that the tight ones are stricter than the loose ones, so it's sort of strict and weak. At least that's the motivating examples, though it could mean other things as well. And so, okay, just a small note. So each enhanced 2 category, of course, has a pair of 2 categories associated to it, the whole one. Sometimes note like this of loose maps, and then you can restrict to the tight maps, but take all 2 cells between them, and then you can indeed characterize the enhanced 2 categories as 2 functors like this with an additional property or 2. I won't bother to do it. But of course there's many examples. So whenever you have a 2 category with 2 kinds of map, one more special than the other, you have that. So for example, monoidal categories, strict and lax maps, or strong and lax maps, or strong and prolax maps, or anything you want. So, or fibrations and Cartesian functors and just lax morphisms, all this sort of stuff. And so this is a very simple definition. So the reason Lack and Shulman introduced it is that they're also exactly enriched categories. So if you look at the RO category of cat and look at its objects or functors, so we only look at those functors which are basically inclusions of full subcategories. So injective and objects and fully faithful. And so this is a full subcategory and it's Cartesian closed. It's an exponential ideal of this. An enhanced 2 category is exactly an enriched category over this F, this category of full embeddings, as they call them. Okay, and so that's the good news, is that it means that we can use enriched category theory to study these enhanced 2 categories, and I'll say a little bit more. But before going there, we can ask what the usual notions of enriched category theory give us. The enriched functors, they're just two functors which preserve the property of tightness, say. And you've got your enriched natural transformations. They're like two natural transformations, but whose components are tight morphisms. Okay? Good. And so the reason that Lack and Shulman introduced F categories, enhanced two categories, is because they wanted to study some funny behaviour of limits that occurs in two category theory about the interaction of like strict and lax maps. Sometimes you only have limits of like comma categories exist when one map is lax and one map is strong or something like that. It's funny. Or you can form the Eilenberg-Moore category of a lax morphism because you don't require a functor between categories with limits to preserve those limits in order for the Eilenberg-Moore category to get them and the projections to preserve them. So this is all stuff that's about the interaction between different flavours of maps. It's quite subtle. There's no subtlety here. We're just going to do... for what I want to tell you about, all we need to do is look at some really simple stuff. So, what tight limits. So these are certain F-enriched limits, but they're just two categorical limits in the two category of tight morphisms, which are preserved by the inclusion into the two category of loose morphisms. Okay, so for example, tight pullbacks. Tight pullbacks, you've got pullback square of tight morphisms. Okay, so two categorical limits, so it should have a universal property for two cells as well. But it also has its universal property with respect to the loose morphisms. Okay? Good. So now we can start to move to sketches. So remember what a sketch is. So it's just a category, some people may say small, I won't, with a collection of diagrams and cones over those diagrams. Okay, I'm not going to go into size things here, and there's some good reasons not to, I would say. So that's the classical definition. So the enriched definition is basically the same thing, but you replace your cones by weighted limit type of cones. So you need to introduce weights. Otherwise it's the exact same. So an enriched category over some V with a collection of now weights and diagrams indexed by those weights and weighted cones which look like that. A bit ugly if you ask me. But just the formalism makes it seem a bit hard to work with sometimes. But otherwise they're exactly the same thing. So that's a enriched limit sketch. And so when V equals cat, you get what I would refer to as a two-dimensional limit sketch. And when V equals F, we get the ones that are of interest to us, which are the enhanced two-dimensional limit sketches, okay? Which are the topic of the talk. And let me just say one more thing. So a model of a sketch, well, often people would look at a model in a category with some limits. There's no reason to do that. You can look at a model in another sketch. You can just say it's a sketch morphism. So that means just a functor which takes the weighted cones to the weighted cones, right? So there's good reasons to do that, actually. Here's just a simple one. You might have a sketch where you were interested in models, but the limits weren't actually limits, or the limit cones, they weren't quite limit cones. They could be like homotopical limit cones or something like that. Or you might just not know that they're limits yet and want to. So that's actually relevant to what we do. So I will speak of models in other sketches. Okay, and so last definition really is categories of models of F-enriched sketches. So I'll talk about the lax case first. So the objects are, just the models. The loose morphisms in the lax case are lax natural transformations in just on the two category of loose maps. So such that when you restrict to tight maps, it becomes a two natural transformation. So in more elementary terms, that means that you have these loose arrows and you have your lax naturality two cells, but these have to be identities for those tight arrows there. Okay? And the tight morphisms are the strictest things you could have, so the F natural transformations. And the two cells is only the same usual option you can really have, which are the modifications. And so this gives a F-enriched category. Okay? And the main thing here is we're saying that if you think back to the double categories case, this concept is picking out which maps like the source and target are to be preserved strictly and the other ones which aren't. So in that case, S and T and the pullback projections will be tight and the other maps will be loose. Okay, and so you've got different flavours of weakness. There's 4 in two category theory: strict, pseudo-lax and co-lax. And we write them like this, building on following the sort of notation of Black and Schulman. And so you can likewise have the F category of models, or say W maps, which involve W natural transformations, where that can mean lax, co-lax, pseudo, or strict. And in each of these is in fact itself enriched sketch, because you can just take the level-wise weighted cones. In other words, you can evaluate a cone, any weighted cone, in here for each T and ask whether that is a cone in C. And so they're the level-wise ones, and that makes it an enriched sketch. And important, I guess one of the reasons we're working with sketches rather than always realized sketches is that even if C has limits of some type, it may be the fact that the F category may not inherit them in this subtle world. So the original thing might be realized and this might not be in some settings. Okay, so here are some examples. So we sort of saw it earlier, but so the sketch for pseudo categories in an F category looks like this, plus some more maps. I think sketches are called sketches because you never write them down in full detail, just sketch a little bit of it. Well, actually people do, but I'm not going to do it here. So this is a tight pullback sketch. It's just got that pullback, it's got one more as well. So if we view cat as an F category with just one kind of morphism, so tight and loose coincide, and all its limit cones, then the models in there are the pseudo-double categories. The models in the world of monoidal categories, strict and strong monoidal functors with its limit cones, are exactly the monoidal double categories. So that's a good example. Here's a simple example. I haven't written it down in much detail. There's even a missing top to that. But that's a sketch for a pseudo-monoid in an F category. The main thing I'm emphasizing here is I want to say things like pseudo-monoid in an enhanced 2 category rather than in a 2 category, which is actually the sort of interesting thing that brings something new, I would say. It's type product sketch, captures monoidal categories, also monoidal double categories, things like that. Here's some more interesting, here's probably my favorite of these 3 basic sketches. It's the sketch for vibrations in an F category. So I'll sort of build it up gradually. So the fun thing is it starts with a tight morphism. The vibration should be tight. And, well, okay, if you want to talk about vibrations algebraically, you need to form the power by the arrow, so like the category of arrows, and also the slice, so the comma object, and then you have this canonical map from the category of arrows to the comma object, like that, remembers the domain. And to say that F is a fibration in a, say, 2 categories to say that this has a right adjoint, right inverse, or yeah. But the point is, we only make this loose because it's like the structural thing that does the Cartesian liftings, and we don't want that to be tight, but we do want the original thing to be tight. So, so this is a type comma object sketch. Models in CAT are, say, Cloven fibrations. In the world of monoidal categories, strict and pseudomaps, these are monoidal fibrations, which is, monoidal fibration is an interesting notion. It's sort of obscure when you see it because you have a strict monoidal functor such that it's also a fibration, and the tensor product of Cartesian maps are Cartesian, so it's a weird mix of strict and universal structure. And in the world of double categories, pseudo-double categories, strict and pseudomaps, these are the double fibrations which were recently introduced as well. And okay, so our main theorem, I suppose, is about models in models. So if you take your different weaknesses, okay, well, you have this bar operation, which what it does is it interchanges lax and colax, because you're swapping the direction of 2 cells, but it doesn't do anything else. And so our theorem is that if you have 3 F sketches, and you have an isomorphism of F sketches, where you look at models and models, models and models, but you have to swap the weaknesses here. You have to, so it's sort of lax and colax, colax and lax. The proof of this is nice. The point is, there's even a biclosed monoidal category of F sketches extending the gray tensor product. Actually, it's more sensible just to think of it as a multi-category because the tensor product isn't too important. But and then this is just the standard isomorphism between the left and right internal HOMs in a biclosed multi-category or biclosed monoidal category. And so applications of this, well, just mixing our basic sketches, the 3 I mentioned, explains lots of perspectives on different sorts of structures in the literature. So just starting with one, and maybe it's not that well known, but like the intercategories of Grandis and Prey, that's what you get when you mix pseudo-categories, and lax maps. Or you can get monoidal fibrations as, pseudomonoids and fibrations, or fibrations and pseudomonoids, but keeping track that some maps are always strict. That's the point. Or monoidal double categories, or double fibrations, or duoidal categories, all these sorts of things are like that. Today I learned about another example, which are the fibered up fibrations, which I think you can get when you mix fibrations, up fibrations, pseudo and lax maps. So you need to, the nice thing then is you can think of a fibered up fibration as a up fibration in a F category. That's the thing. So if you want to, if you want to understand some of these complex structures in an internal sort of way, that's the idea is we do this. So further applications are that it actually clarifies the study of 2-dimensional limit theories, building on work of Parr and Lack. I won't go into that aspect. And there's a forthcoming paper. Here it is. There's some references. I could also mention the work of Marek Zawidowski on lax monoidal fibrations, who sadly passed away, but that seems to fit into this world when you mix skew-monoidal categories, fibrations, and lax maps. That seems to sort of be very close to what he was doing, and I think it deserves another look at that sort of stuff. But so it's a couple of references, and that's the end of the talk. So thanks very much.
Thank you. Are there questions or comments? Please.
Yeah. So since we have enhanced the sketches, do you have a title about what multiply enhanced Cavalier modality for them?
That's a very good question. No, I think that's no. We haven't thought about it, but I think it's a very good question.
Jenny?
Thanks. I have a more basic question. Are there any examples where the tight and loose maps aren't exactly strict versions, a strict version of something weak, but are just a generalization that's not exactly strict, which is like functions and relations or functions and so forth?
Yes. So functions, relations, because it's actually a two category strict one. Is an example with the orders on the two cells. So F categories correspond to certain double categories in which every map has sort of, is it a companion and conjunct? There's sort of strictification of those. I think my collaborator Nathaniel knows more about those double categories than me, but so things like profunctors and so on are basically almost F categories, but they're sort of slightly weaker ones. And certainly those sorts of things fit into a slightly generalized version of this story that would be relevant, but we haven't looked at, say, models in slightly generalized F categories.
So, thank you for the talk. So if you look, for example, at bicat with homomorphism, or if you look, say, at hom k cat with the pseudo-natural transformations, then it's true that if I look at a vibration in your satir, so it's a strict map, which is a vibration, then you can actually take pullbacks along that. I just wondered if maybe there's some way in this sort of setup of seeing why those pullbacks, which should really exist, do exist in that way.
That's a good question. I don't have the answer. What I will say is my co-author and PhD student Joanna, who she will talk later in the week about enhancements sort of this picture to the infinity category worlds, where then what play an important role are the sort of pseudo maps, which are also fibrations, and then you form in like pullbacks of things and stuff in that kind of setting is relevant. So I feel like when you start mixing this with the infinity, but I just don't fully understand.
Okay, I have just a detailed question. This sketch of pseudo double categories gave on one hand pseudo double categories, on the other hand, when you look at monoidal double categories.
Yes.
Is it then you use this pseudonym, or is it monoidal pseudo double categories?
Right, so in this thing everything was supposed to be pseudo, if I'm not sure if I said it quite right.
Could you say a bit more about the gray tensor product of sketches? If you have tight maps, you need a pseudo square, something like that.
Right, so, well, there's a few variations. For the one I talked about here, you would want to form the usual, say, lax or pseudo-gray tensor product, but when you have tight morphisms, the square should strictly commute. So you should have identity there. That's the only quotienting you have to do. That gives you a tensor product of F categories, which is an extension of the gray tensor product. And the good news is to extend it to a tensor product of F sketches. All you have to do is sort of add some limit cones, right? And you just sort of take the horizontal and vertical ones.
Okay, so if there are no more questions, let's thank John again.